Okay, so we're going to take a look at post-lab assignment one. The goal of this is to give you a resource where I walk through or we walk through the entirety of the problem or all of the problems so you don't have to worry about getting it wrong. Um, with that said, please make sure you take a look at this and try to accomplish these before taking a look at this video. Use this to clarify, use this to understand, but don't use it to do the work because you're going to have to be capable of this. Okay, so off we go. So for this post-lab assignment, the first little set of we're going to be collecting data from solution. So in the pre-lab, it asks you to do a calculation for the amount of KCl in order to make, I think it was 10 mils of a 0.2 molar KCl solution. And if you did that calculation correctly, the mass of KCl turned out to be 0.1491 grams. Easy enough to measure. Um, so that's the mass we would have. So we're going to need that. The volume of water, it's not, I guess not, it's going to be around 10 mils, but I'm just going to put that there. Um, and when we're doing this, you weigh the empty vessel, you weigh the empty graduated or volumetric flask, I should say. All right. You weigh that empty, you put your salt in, you fill it up with water to the line, and then you weigh it again. And so the difference of that and the empty flask is going to be the mass of the whole solution. So we're going to use a value of, I'm just going to use 10.500 grams for that. So let's just pretend that's what it got. It should actually be less than that, but let's pretend the mass of solution after you subtract the empty flask is 10.5 grams. Okay, so that's the information that we have from part one. So I'm asked to calculate two things. One, I'm asked to calculate the molality and the percent mass of the KCl. So let's start with molality. Molality is lowercase m, and I always tell my students to start at the end. Let's start at where we need to go. So I know what I need to solve for. So instead of writing down all the numbers I have and making a decision, let's just go to the end. So I know that I need, for molality, I'm going to be moles of solute over kilograms of solvent. That is actually pretty important because the solute versus this in the solvent for molarity, capital M, you would need moles of solute. And in this case, my salt solute is KCl. But if it were molarity, I would need liters of solution, the entire, and we have that. But actually, our solvent, it's kilograms of solvent, and in this case, it's water. We're going to use molality a lot when we're doing colligative properties calculations. So just recognize that kilograms of solvent, not solution. All right. Do we have either of those? I've got a mass of KCl, so we can probably turn that into moles, but we don't have it directly. Do I have kilograms of water? No, I have kilograms of solution. So we don't have anything directly. There's nothing we can plug in. So let's first try to solve for moles of KCl. Lowercase n is typically what we use, or it is what we use for the variable for moles. So moles of KCl. This is a simple conversion, 1.491 or 0.1491 grams of KCl times a fraction, grams to go away, moles to remain. 1 mole of KCl is 74.55 grams. This is the molar mass of KCl. So I end up with 0.00200 moles of KCl. I'm gonna mimic, I guess, one more zero actually. I need 4 sig figs because I started with 4 sig figs. So there we go. So there we go. We have our moles of KCl, so I can actually just plug that number in. So I ended up with 0.002000 moles of KCl. So now all I need to solve this problem are kilograms of solvent. So how do I get kilograms of solvent? Well, we have the mass of the solution. which is 10.500 grams. We know the mass of the solution is made up of the mass of the solute plus the mass of the solvent. Well, we know that I have 0.1491 grams of the solute, and now I can solve for mass of solvent. So the mass of my solvent is 10.5 minus the 0.1451 gives me 10.355 grams of the solvent, which is my water. And I can now plug that in. So 10.3. Oh, before we do that, this is in grams. I need to convert to kilograms. So grams in the bottom, kilograms in the top. 1 kilogram is 1,000 grams. So I'll divide by 1,000, or I'll just move the decimal 3 spaces. So we end up with 0.010355 kilograms. That's a 5. There we go. Do the math, and you end up with a value of 0.1931 in lowercase m for molality. All right, molality is solved. So the next step is determining percent by mass. So percent mass of KCl is always the part over the whole. So mass of KCl over the mass of the KCl plus the mass of the water times 100. We know the mass of KCl, 0.1491 grams. I know the mass of my KCl, 0.1491 grams. And I did determine the mass of the water, 10.355 grams times 100. And we can recall that that was 0.1491 grams all over 10.500 grams times 100. Grams is going to cancel, and I am going to be left with, after I do the math, there should be no unit. Well, kind of 1.4%. That is the quantity that we're going to end up with. So 1.4% is what you end up with. 1.4% KCl by mass. All right, moving on. This next one's a little more involved. I'm going to think about it a little bit more in terms of the ways that we can solve it. So let's first of all determine what the actual goal of this is. So explain how to create 100 mils of a 0.25 times 10 to the negative 5 molar solution of NaI. We can only measure volumes in a range from 1 to 10 mils, and we have volumetric flasks of 10, 50, and 100 mils. So how do we solve this? So first of all, what do we need? Our goal, I should say, there we go. Goal is to achieve 100 mils of a 2.5 times 10 to the negative 5 molar solution. Can I do this right out of the gate? The question is do I need all that glassware, or can I just simply weigh out enough sodium iodide to create this solution? Let's try it. So we're going to grab ourselves a 100 milliliter volumetric and in hopes of putting in some amount of potassium iodide, filling it up to the line, and having our solution. Is it possible to do that? Well, let's find out. So I want to make 100 milliliters of this solution. I want that solution to, so 2.5 times 10 to the minus 5 moles per 1 liter. Right now, the liters will not cancel, but I can actually change that. We're just going to call that 1,000 milliliters. Those two are the same, so I can replace one with the other, but this will allow milliliters to cancel. So right now, that's going to give me moles. Remember, this is concentration of the NaI, my target concentration of the NaI. So it's really a conversion. Concentration is simply a conversion between moles and volume of solution. Okay, so right now that would give me moles of NaI that I would need. I'll write that in, NaI. I want moles of NaI to go away. I want grams to remain. 1 mole of NaI is, I looked this up, 149.894 grams. This is the molar mass of NaI. When I do the math, what I find out is my final mass is 0.00037 grams of NaI. It is impossible to measure that accurate. I mean, you can probably measure it to the fourth decimal place, but nothing beyond that. And it's not really going to be all that accurate to begin with because you're not sure you got this is a very, very small amount. So we can't measure this, cannot measure. It's just too small a quantity to measure on a balance. So we cannot do it directly. So at this point, we have two options. Option one, we start with the goal and work toward a mass, a usable mass. Or two, we just start with an easily measured mass and then work towards that final solution that we want to make. So we're going to do the second one. We are going to work towards that final, the end solution that we're looking for, that 2.5 times 10 to the minus 5 molar. And we're going to make a quantity that's going to be easily measured. The reason that we're actually going to use this second one is the second choice here is because we can keep doing dilutions if we need to. We can just keep doing dilutions along the way if we need to. Also, if you work in the other direction, if you want to work in the other direction, you have to get the number, the mass exactly. And so we want to start with an inexact mass and kind of decide based on volume, because we can really accurately measure the volumes with these volumetric pipettes. So we want to work in that other direction. So let's say that we wanted to measure out, I don't know, 0.25 grams. So let's say that we wanted to start with 0.25 grams. That's easily enough measurable on the balance. And of course, you're going to go to the balance and you're going to actually measure it out. I want to get to this next page. And what you end up with is, let's say, 0.301 grams of NaI. So nowhere near your starting balance. And again, this is why we do it in this direction. It's easier to kind of do it in this direction. We're going to check it along the way as well, but that's the idea. So we're going to start with 0.301 grams of NaI. Perfect. So we want to figure out how many moles this is. So we're going to do a calculation using the molar mass of NaI. NaI, there we go. 1 mole. Grams, that's the molar mass. Grams cancels. I end up with 0.00201 moles down to three. I rounded it to 3 sig figs. Moles of NaI. Great. But of course, we're going to take this and we are going to put it into a 100 milliliter volumetric. So there's my 100 mils. I'm going to put my 0.301 grams in there. I'm going to dissolve it. So I need to divide by 0.001 liters or 100 mils. And I end up with a concentration of, let's see, what is this? 0.0201 molar. And this right here is my stock solution. So I have my stock solution, my starting point. And so now we are going to see every step of the way, we're going to see, is it possible to get to my target? So can I take a small quantity of my stock solution and get to my target? So we're going to do this by doing a first dilution. So first dilution. Whenever we're doing a dilution, we are going to use the equation V1C1 equals V2C2, or M1V1, any version of that. Concentration times volume equals concentration times volume. So my stock solution and my first dilution. So the question is, can I make it directly? Can I achieve 2.5 times 10 to the minus 5 molar? That's the question. So what volume do I need, considering I have a concentration of my stock solution of 0.0201 molar? I am looking to get 100 mils of my 2.5 times 10 to the minus 5 molar solution. So this is just simply asking how much of the stock solution put into a 100 milliliter vessel. Let me just, my drawing is bad. There we go. So if I were to take this and put it into a 100 milliliter vessel and fill it up, could I reach what I'm looking for? So we're going to do those calculations. So 100 times 2.5 times 10 to the negative 10 to the negative 5, all divided by that 0.201. Doing this problem, you end up with a volume of 0.124 milliliters. Molarity cancels, we're left with just mils. I cannot measure 0.124 mils. I can only measure between 1 and 10. So this does not work. So I cannot do this. I will still move some of the stock to a 100 milliliter vessel, but we have to think about it. We need to do a second dilution. So let's move back to this first dilution again with this stock solution. Okay. Let's do V1C1 equals V2C2 again. My volume, let's just move 1 milliliter of my stock solution. So we are moving, literally putting in 1 milliliter of the stock solution, then diluting it to 100. So 1 mil of my stock solution, 0.0201 molar. Okay, so 1 mil of my 0.0201 molar. The volume 2, we do know we're going to dilute it to 100 mils. Let's make it as dilute as possible. The question is, what's the new concentration of my first dilution going to be? So again, move the 100 mils to the other side by dividing, and what you end up with is 2.01 times 10 to the minus 4 molar. There is my concentration. This is my dilution 1 concentration. And we did that by moving 1 mil of the stock into a vessel, filling it up, mixing it. There we go. So now, with that new solution, we are going to create another one. We are going to do a second dilution. We are absolutely going to be able to make it for this next step. So let's try again. V1C1 equals V2C2. So we are going to take, we are interested how much volume from the new concentration, which is 2.01 times 10 to the negative 4 molar, in order to make, we wanted to make 100 milliliters of this 2.5 times 10 to the negative 5 molar solution. Okay, so do the math. My volume 1 turns out to be 12.4 milliliters when we do that concentration. So essentially what we're going to do is we're going to take from dilution 1, right? We're going to take 12.4 milliliters. We are going to place it into another 100 milliliter flask. We're going to fill it up to the line, and we have our new dilution. So 12.4 mils of dilution 1 into a fresh 100 milliliter flask. 12.4 is outside of the range of 1 to 10, but we could do 10 mils, then 2.4 mils. Certainly could do that. If we wanted to, we could make two 50 milliliter ones, and that would cut that volume in half. But this would work. We would accomplish our goal by doing this. We can't get below 1 mil. That's impossible to do, but we can do twice that. So it's always better to transfer a larger volume than a smaller volume. So yeah, this would work. Moving a dilution, or the second step, we could have slowed it down and done a little bit less. But that's the idea. Just kind of taking it stepwise. Okay, can't make the solution directly, so let's try with the first dilution. Okay, we got to do one more. So you can kind of work your way towards it. There is no rush to get there. All right, next up. Now, this is all downhill from here. So if we take a look at calculate the molarity of a solution, okay, so that's our target, molarity of a solution made by dissolving 25 mils in 6.1 to a volume of zero point 0.5 with water. So really important here. That 0.5 liters is the volume of solution. Because if you imagine how this is made, you take a 500 milliliter volumetric, add the 25 mils of concentrated HCl, then finish it off with water. So it's important to measure that I'm not adding 500 mils of water. I am finalizing that solution. So essentially, we are looking for molarity. By the way, there are two ways to do this as well, but let's look at think through the first one. So molarity, capital M, is equal to moles of solute, liters of solution. We know that the solute in this case is HCl and liters is liters of solution. Do I know either of those? Yeah, I actually do. I do know that we are going to end up with 0.500 liters, so I can plug that in. This question is not about what the molarity is. The question really is, hey, how many moles of HCl do you have? When you have a concentration, this allows us to convert between moles and liters of solution. That's what we should use a concentration for, because dimensional analysis, well, if I start with 25.0 mils times fraction moles per liter, 1 liter is equivalent to 6.15 moles. Of course, I can just call that 1,000 milliliters. It's going to skip right through that conversion. Mils cancels. We end up with 0.154 moles of HCl. Well, that moles of HCl, we can plug it into our molarity, 0.154 molar moles per half a liter. That is equal to 0.308 molar. There we go. There's the answer. Let me highlight the answers here. Boom. Boom. And those are highlighted. Perfect. Okay. So we end up with 0.308 molar. Good. Okay, that's it. We can move on, right? Yeah, absolutely. Or we could have just recognized the fact that this is a dilution. Whenever you have a dilution, we can use V1C1 equals V2C2. So my volume 1 is 25 mils of my solution at a concentration of 6.15 molar. My volume 2, actually we know that, 500 mils or half a liter. What is the new concentration to be? Well, just do the math. What you're going to find out, 0.308 molar. Again, either one is going to work. So there we go. That's how we do those conversions. If you recognize it's a dilution, you can just jump straight to C1V1 equals C2V2. All right, next up. The concentrated HCl is 12 molar and 36.0% HCl. So concentrated at 12 molar and 36% HCl by mass. What is the density? Again, we are going to start at the end, the density of the solution. We're going to start at the end. So D is equal to mass of solution, or I should say grams of solution, over volume or milliliters of solution. Do we have any of those? In fact, we don't really have any quantity at all. There's no mention of mass or volume of either of these. And so we get to make an assumption. Whenever you have a percentage, the easiest assumption to make is, hey, let's just assume 100 grams. Because if I assume 100 grams, then percentages becomes a mass. So if I assume 100 grams, well, 36 grams of it is HCl. 64 grams of it is water. And total, if we add those two up, we are going to get 100 grams of solution or HCl. So when you assume 100 grams, it makes it much simpler to just makes it much simpler. All right. So now, do I have any of the data? Yeah, I said that I have 100 grams of solution in this scenario where I'm assuming 100 grams. Because we're talking about concentration, we can assume 1 gram. You can assume 10,000 grams. It's just easier if you pick an easy number. Okay, 100 grams. So all I really need to know is the volume of solution. That's where molarity is going to come in. Again, remember, molarity is going to allow you to convert between moles of, in this case, HCl and liters of solution. Well, that means that in order to get liters of solution, I need to get moles of HCl. Can I do that? Absolutely, we can, because we have 36.0 grams of HCl, which I can use the molar mass of HCl. Grams over moles. 1 mole of HCl is equivalent to 36.461 grams. Grams of HCl cancels, leaving me with moles of HCl. Now I can use that moles to liters. 1 liter is 12.0 moles. This is going to give me liters of solution. And then we can do a quick conversion times 1,000 milliliters over 1 liter to do the conversion into mils. I end up with, if I do the math, 82.3 milliliters of solution. So 82.3 milliliters of solution. My density turns out to be, concentration. Or did I skip a, no, I didn't. I'm looking for density. All right. So turns out to be my density is 1.22 gram per milliliter. There we go. That's how we do it because we had mils of solution based on that concentration. Perfect. All right, moving on. So 2 left. A 1.38 molar solution of nitric acid in water, okay, has a density of 1.04 grams per milliliter. What is the mole fraction of nitric acid? Again, I am not given any amount. So we have to assume a quantity. I could assume 100 grams, but there's no percentage here. So what quantity do you want to assume? Again, we can assume anything that we like. I am going to assume 1 liter. Why assume 1 liter? Well, I know that molarity is 1.38 moles of nitric acid, HNO3, per 1 liter of water. So if I assume 1 liter of solution, not water, I'm sorry, solution, I can assume that I have 1.38 moles of HNO3 and I have 1 liter of solution. Perfect. So we have a liter of solution, 1,000 mils of solution. We might use that, or 1.38 moles of HNO3. So again, we're going to start at the end. Mole fraction is equal to moles of HNO3 over moles of HNO3 plus moles of water. Not times 100. This is going to be a number between 0 and 1, but I just need to figure out moles. Do I have any of those? Absolutely, I do. I guess I'll do it up here. I have 1.38 moles of HNO3, 1.38 moles of HNO3. So really all I need is the moles of water. That's the only thing that I'm missing because we have these. I don't know this. That's all I'm looking for. Okay. So how do we figure this out? Um, so we have concentration, we have density. Density is going to be the key here. Uh, all right. So let's start with the fact that we have a density of 1.04 grams is equivalent to 1 milliliter of solution, right? We just did that. So what we can say is, how much do I have liters or grams of solution? Yeah, I have 1,000 milliliters or 1 liter of solution. 1,000 mils times fraction. I want mils of solution to go away, and I'll have grams. So 1.04 grams of solution is equivalent to 1 mil. Mils cancels, leaving me behind grams. 1,040 grams of solution. Great. Now that I have solution, um, remember the solution contains both the mass of the HNO3 plus the mass of water. So in order to get moles, I need to isolate the water. Well, because we know that I have 1.38 moles of HNO3, I can actually figure out the moles to grams. The molar mass is 63.013. That's the molar mass of the HNO3 to 1 mole. I actually have, when I do the math, 87.0 grams of HNO3. Okay, we're almost there. So what I now know now is using the numbers that I have 1,040 grams of solution. The mass of my water plus the mass of my nitric acid, which is 87.0 grams. So the mass of my water, and I'm just going to put this up here, mass of the H2O after I do that math turns out to be 953 grams of water. Well, I'll take that 953 grams of water, grams to moles. 1 mole is 18.015 grams. Grams cancel. I end up with 52.9 moles of water. I can plug that in up here. So 52.9 moles of water. I end up with a mole fraction of 0.0254. Okay, so to recap, we assumed 1 liter. That gave me moles of HNO3 right away. I figured out that mils can be converted into grams. Density allows you to go between grams and mils of volume and mass. I have 87 grams of acid, 1,040 grams of solution, allowing me to figure out the total mass of water. And then we can convert that to moles. Problem solved. All right, last one. This one feels very complicated because this is a gas law problem. So, kind of a gas law problem, but let's take a look. All right. Exactly 400 mils of a monoprotic acid solution. So monoprotic acid means one hydrogen is acidic. So whenever I do monoprotic, I'm just going to do HA, some anion with it. Okay, so some acid. Doesn't matter what type of acid. We're going to have excess zinc. So zinc metal, we don't really have to care about it. It's just there to run a reaction. Evolves 2.43 liters of hydrogen gas measured over water. This is going to be important at 21 degrees Celsius and 747.5 torr. So that's the atmospheric pressure. The vapor pressure of water is 18.6. We're going to talk about how that's relevant in just a little bit. Okay, so again, let's start at the end. We are looking for what is the molarity of the acid. So in order to get the molarity of my acid, I need two things. I need the moles of acid present over the liters of solution, acid solution. Do I have either of those? I do. I have 0.400 liters of my acid solution. That's right here. Okay, so I have zero point 0.4 liters. Great. So this question is not asking for molarity, although it is. It's simply asking, hey, how many moles of acid do I have? Do I have any indicators, any information about the acid? Well, I have volume of gas, not, uh, I don't have any other information. All I have is a volume of my acid, and that's it. Okay, so what this means is if I have one chemical, and it is not the chemical that I'm looking for, this is a stoichiometry problem. So what we have done is we're going to say, all right, I have mixed zinc solid with my acid. It has produced hydrogen gas and some other stuff. Ultimately, we don't really care what it produces, but it's going to produce zinc plus two A's attached. If it makes it easier, we could call this HCl. HCl would be a way to say it, but in any event, so two A's. If I balance this out, really what's going to happen is this. Two acids for every one hydrogen. This is the molar ratio, two HAs to every one H2. So what this tells me is if I know the moles of hydrogen, I know the moles of acid. Knowing the moles of acid means I can plug it in above. So this is a stoichiometry problem. But hydrogen's a gas. I can't calculate the mass of it and convert that to moles. So when you have a gas, we use PV equals nRT. PV equals nRT is how we convert between the volume of a gas and the moles. Volume in moles is what we typically use for this conversion. I'm going to solve for moles because that's what we're looking for. So moles of my gas is going to equal to pressure times volume all over R times T. So let's see if we can just plug in what we have. We're going to come back to pressure because that's going to be an important one. We know that the volume of gas, not the 400 mils, because we already have that taken care of, was 2.430 liters of the hydrogen gas. You can see that right here, 2.43 liters of hydrogen gas. My R value, we should know this. This is a constant, 0.08206 liters times atmospheres, moles times Kelvin. My temperature has to be in Kelvin. It's 21 degrees, so 273 plus 21 gives me a value of 294 Kelvin. So 294 Kelvin. Now the pressure. The pressure is going to be the frustrating part. So I just want to walk through quickly what this looks like. So if I have a reaction vessel, so here's my flask running the reaction. I've got my zinc piled on the bottom in my 400 mils of acid. It starts to produce a bunch of hydrogen gas. That hydrogen gas fills up, and if we didn't have any way to gather it, we would lose it. So we connect a tube, place it underwater, and we put it into an upside down collection vessel. So this is all essentially underwater. Okay. And what happens is as this fills up with gas, all of the water that was in this vessel gets collected. So this up here is my collection of hydrogen. This is the water that slowly gets pushed down. In here, I've got hydrogen gas. But actually, anytime you collect over water, you also have water vapor. So this is where the pressure change comes in. So the total pressure of the atmosphere pushing down is equivalent to the pressure of the hydrogen gas plus the pressure of the water. So if we look back at our problem, we see that we have 747.5 torr of atmospheric pressure, 747.5 torr is equal to the pressure of the hydrogen. That's what we want, plus the, I think it's 18, let me check, yep, 18.6 torr of the vapor pressure of water. So subtract those. So the pressure of the hydrogen and the pressure of the water gives me total vapor pressure. So what we end up with is doing the subtraction. My pressure of H2 is equal to 728.9 torr. I can't have it in torr. I need to get rid of torr and replace it with atmospheres. One atmosphere is 760 torr. Torr cancels, and I end up with 0.9591 atmospheres. So I can plug that in, 0.9591 atmospheres. Do the math, moles of H2, I end up with 0.0966 moles of hydrogen. Okay, almost there. So if I have 0.966 moles of hydrogen, I have to recognize that what's going to happen is I have to think about stoichiometry. I'm going to have twice as much H2 as I do hydrogen. So 0.0966 moles of H2 times fraction. Using molar ratio, I want moles of hydrogen to go away. I want moles of my acid to remain. 1 mole is equivalent to, sorry, that backwards, 2 moles of acid to 1 mole of hydrogen. Moles of hydrogen cancels, and I end up with point, what is it? 193 moles of HA. So I can plug that in, 0.193 moles of acid. Doing the math, we end up with 0.483 molar. There we go. Long way around, but anytime you have a gas, you can always use PV equals nRT to solve what you need. So there it is. Long-winded, but that's the walkthrough. Hope you answered it. Any questions, feel free to ask your professors or, yeah, shout out here to come to me for help as well. All right.